All right, today we are diving into a really cool breakthrough in AI that is fundamentally changing how we predict the future. It's a model called MOIRAI-MOE, and it represents a whole new way of teaching AI to become a specialist in forecasting, well, pretty much anything.
Okay, so let's just jump right into this. For years, the holy grail in AI forecasting has been this idea of creating a single universal model. I mean, imagine one algorithm that's powerful enough to predict everything from stock prices to energy demand to website traffic, all without needing to be totally rebuilt for each different problem.
So yeah, the dream is this universal forecaster. But the old way of doing things, building a completely separate, custom-made model for every single dataset is just a nightmare. It's incredibly inefficient and it just doesn't scale. So the big question has always been, why is this so dang hard to do? The core problem, the real villain of the story, is something called time series heterogeneity. Now that's a fancy term, but all it really means is that time series data is, well, it's wild. It's all over the place. Unlike text or images, which have pretty standard structures, this data comes in every shape and size imaginable. Different patterns, different sample rates, hourly, daily, weekly, you name it. And it's this sheer variety that makes a one-size-fits-all model so tough to build. Now, here's where it gets really interesting. It turns out that our go-to method for trying to categorize all this data, its frequency, is often super misleading. The researchers behind MOIRAI-MOE had this key insight. Just because you label a dataset hourly or daily doesn't actually tell you that much about its real patterns. And this slide just nails it. You could have an hourly dataset that looks almost identical to a daily one. And at the same time, you could take two different daily datasets and they might behave in completely different ways. Oh, and to make it even harder, a single time series can just change its own patterns over time. So yeah, relying on that frequency label alone, it's just not going to cut it. So, this brings us to the first real crack at solving this problem, a model called MOIRAI. You can think of it as a really clever first attempt. Let's call it a toolkit, but one where all the wrenches are a fixed size. It was a smart design, but it had its limits.
So MOIRAI's main idea was to have all these different input and output layers, with each one custom-built for a specific frequency. So if you had hourly data, you'd use the hourly layer. If you had daily data, you'd use the daily layer. It basically forced the model to manually pick a very specific, predefined tool for each job.
The researchers themselves called this a human-imposed heuristic. In plain English, that means it's a rule that a person came up with, not something the model learned on its own. And that rigidity became its biggest weakness. I mean, what happens if the human gets it wrong, or if the data doesn't fit neatly into these little predefined boxes? And this is where the evolution happens. This is where things get really exciting. Enter MOIRAI-MOE, which brings in this powerful concept called a mixture of experts. So instead of a toolkit with fixed wrenches, I want you to imagine a whole team of specialist mechanics who just automatically know the right tool for any job that comes their way. Now, this comparison right here tells the whole story. On the left, you see the original MOIRAI with all its separate, rigid pathways for each frequency. But on the right, MOIRAI-MOE is so much cleaner. It's got this one single streamlined input that funnels all the data into a dynamic mixture of experts layer. It is a complete shift from rigidity to flexibility. So what in the world is a mixture of experts, or no? Well, it's an architecture that has multiple little specialized mini-models, and we call those experts. But the real magic is in the gating function. It acts like a super smart traffic cop, looking at every single piece of incoming data and dynamically routing it to the one or two experts that are best equipped to handle it. And this brings us to the most important shift of all. The model is no longer specializing at this big, clumsy level of frequency. Instead, it is achieving token-level specialization. That means it can now adapt its approach for every single data point or token that it sees. It's just infinitely more granular and way more intelligent.
But how does that traffic cop, that gating function, learn to make such smart decisions? How does it know where to send what? Well, this right here is the secret sauce that makes the whole system work.
See, instead of learning its routing rules from scratch, MOIRAI-MOE uses a much smarter method called token clustering. First, it analyzes all the token patterns from the original pre-trained MOIRAI model. Then it uses an algorithm to find these natural groupings or clusters within that data. Each expert is then assigned to one of these specific data clusters. So finally, when new data comes in, it's automatically routed to the expert whose cluster is the most similar match. It's like giving your mechanics a head start by pre-sorting all the tools for them. It's brilliant. Now, when the researchers looked under the hood to see what these expert layers were actually doing, they discovered something fascinating. They described it as a hierarchical denoising process. The model was basically systematically filtering out noise, one layer at a time.
And you can see that process illustrated so well right here. In the early or shallow layers, lots of different experts are active. It's a party. They're busy dealing with all the noisy, high-frequency, super-specific patterns in the data. But as you go deeper into the model, the activity gets much more focused. Only a few key experts are being used, and that's because they're modeling the clean, general, long-term trends. So what this all means is that the shallow layers tackle the noise, while the deep layers find the signal. This creates what's called a frequency invariant representation. It captures the true pattern regardless of the sampling rate. And what's wild is that this is the complete opposite of how a mixture of experts works in language models like GPT. In language, the early layers learn general grammar, while the later layers specialize in specific topics. Here, it's the reverse. All the specific, noisy work is done up front, so that the later layers can focus on the general, clean signal.
Okay, this all sounds great in theory, but does it actually work? Let's look at the numbers, because the results, well, they really do speak for themselves. This new architecture isn't just a little better, it's faster, and it's way more efficient.
First up, a massive 17% performance improvement over its predecessor, the already powerful MOIRAI model. Now, in the world of AI forecasting, an improvement of this size on established benchmarks is a huge leap in accuracy. And it achieves this while being incredibly efficient, because the MOE architecture only activates the specific experts it needs for any given task. It's not using the whole model all the time. This allows it to outperform some competitors while using up to 65 times fewer active parameters. That saves a significant amount of computational cost.
This chart shows the aggregated error for different models, and remember, lower is better here. You can clearly see that MOIRAI-MOE not only beats its smaller predecessor, but it also outperforms the much larger MOIRAI large model. This is just proof that this smarter, more specialized approach really works. This is where it gets really impressive. This table shows zero-shot performance. That means testing the model on datasets it has never seen before in its life. And as you can see, MOIRAI-MOE consistently comes out on top. This proves it hasn't just memorized its training data, it has learned to truly generalize and understand time series patterns.
So, what's the big takeaway from all of this? We are really witnessing a fundamental shift in AI model design. We're moving away from these systems that rely on rigid, human-defined rules, and we're moving toward truly intelligent models that can learn to specialize all on their own. And that leaves us with a fascinating question. As we give AI the power to find its own experts and specialize automatically, what new capabilities are we going to unlock? What happens when our machines become better at organizing their own learning than we are? It's a future that models like MOIRAI-MOE are helping to build right now.